me try to go to everyone. We cannot hear you. Okay.
So I got your document.
Pardon, Dung, I'm not copying you very well.
Oh.
Can you repeat?
I got your document that you sent me.
Okay. Are you able to enter into the website?
Yes.
Okay, so do you see, you do see the pages with the PDF files? I'm renewing part of them, so, but I will update them on the Moodle website. Okay.
Yes. So please wait me 5 minutes.
What?
No.
Okay, fine. Today we will try to use this old blackboard, and I will try to use also an experiment, a whiteboard using my iPad, because sometimes I'm going to lecture from my private studio. We will see. Jacobu is coming back. Okay, let's wait a couple of minutes. You move the recording from iPad here, so I can use. Okay, and whiteboard. Just a second, and then I'm going to share my screen. Whiteboard. The operation couldn't be completed. Why? Quick time. Jacobu, are you there? I think it's time to start. Jacobu? If not able to speak, at least are we able to listen? No reaction. Okay, Dung, you're there. Aurora, you're there. Jacobu is missing. He's lost in some connection. Jacobu, I guess that you're lost. Okay. Okay. Jacobu, now we can see you. I guess that you are at the Adriatico. Okay. Well, your volume is very low, but by the way, I don't care about that. What is important is that you are able to listen. And now let me open today's lecture, that is going to be a sort of a very quick survey about, let's call it fractures and folds. And again, later we're going to consider the kinematics of this very important topic, because most of the work that you're going to perform about dynamics of the folds, you will do that with Karim, as I told you. By the way, maybe we are ready. Jacobu, are you okay? Use your hand. Okay, good. So we can start. Where to start from? Well, maybe sharing my screen, hoping that everything is going to work here. And you should be able to see this. Do you? Do you see a presentation with a beautiful title there? Okay, good. Now, yes. Of course, please interrupt me if something wrong is happening here in the virtual world. Okay, what we're going to discuss today is really a very quick view about basic dynamics of an earthquake. And it's a terrible, complicated topic, but we will take a sort of a shortcut as an introduction for the kinematics that we're going to discuss from Friday on. And that will be tough. That will be tough. So today is more qualitative, and we will go very fast through some basic concepts that could be qualitative or quantitative. Actually, the quantitative part today will be quite easy. It will be sort of a recap of a Coulomb failure criterion. And we will try to put some order about the stress conditions that actually are the tectonics, are the dynamics that we discussed on Monday, that are causing a slip on a fault. And the slip on the fault will be our next focus. So today's purpose is to try to put a sort of a framework where we can enter and develop kinematics of the rupture. We're going to use very simple concepts, and we're going to use also some concepts that I'm sure that you have discussed during some of you during the wave physics course, and I'm referring to the stress and strain, let's call it Hooke's law, and generalized Hooke's law. I'm asking for a confirmation from the diploma students. You know what is a stress?
Yes.
So I'm sure that Lapo
Yes.
developed with you also some operations that you can do with stress and its relation with strain. And usually we use it, okay, but that's the basic also in fluid dynamics to use the, in continuum mechanics, the stress tensor is something very, very important. It's the tensor version of pressure, of course, and its relation with strain. And we can call it Hooke's law. Well, Hooke's law is one view of continuum mechanics, and it's fine. Actually, I'm living with Hooke's law because I'm trying to solve velocodynamic equations for a wave equation. But today, we have to overcome Hooke's law, and nature is overcoming almost every day with different rheologies. And different rheologies like plastic rheology, but it's not our topic for today, and brittle rheology. So something that is going to break and something that is going to fracture. And if you continue to push the system, okay, you will have a sort of a stick-slip cycle of motion. And so this will cause a series of rupture processes on faults. Okay, let's start looking at a very simple picture, very simple. And sharing is paused. Bring your shared window to the front. What do you see now? Christian, stop sharing. Bring your shared window to the front.
Can see your screen.
You can't see my screen.
We can see.
You can see?
Yes.
We can see.
Okay, but which, yes. Okay, what are you looking at?
Right now we are looking at the rupture process.
Okay,
rupture process.
That's fine. You know why? Because I'm receiving a strange message from Zoom, but I guess it's wrong. Okay, now, it's a terrible cartoon, very low resolution cartoon, but this is what we have to study in this course. Now we have a beautiful plane, could be a fault plane. We're going to use actually a couple of angles to describe this plane. We will call them at the end of today, strike and dip. And this is a very useful notation or terminology to depict a plane in space. Another version that we're going to use to describe a plane in space will be its normal. So I think you can see it, just a piece of this screen here. So we can use strike. Definition is coming later. Compared to the surface, this will be called dip. We will have a third angle, but we will call it slip in a very simple approximation. But what we can use is also a vector that is the normal of this plane. So a normal of this plane will correspond to two angles in normal terminology, strike and dip. Now, what's next? What's really important for us is that due to some dynamics, rupture will start. Slip will start. And for a pure tectonic earthquake, we will not study detachment of the two sides, of the two blocks that are over the fault. rupture will start, slip will start with different amplitudes and angles. We will take an average of this. We will begin to discuss this on the next lecture, and then the rupture will stop. So it's the rupture process. We have seen on Monday, we saw on Monday, a beautiful animation about the Hooke event, one possible representation, where the rupture was starting, propagating to the north, then stopping there, continuing to the south, and generating the beautiful, but tragically beautiful, time series that we have seen along the coast of Japan. So rupture is a process that takes place in space and time. And for let's say, a mega event, magnitude 9 event, it could take up to a couple of minutes, and it's going to expand over, let's say, 1,000 kilometers. So it's a huge process. Well, at the end of a kinematic story, we will squeeze all this information in one point, and we will make a point source representation of this process. We will call it point source approximation, and we will see the conditions that we have to assume to make this approximation. So that's the next story. This is, how to say, the prequel of what we're going to discuss from next Friday. So kinematics of the rupture. Today, we will spend 1 hour discussing about what is causing this. Okay, so the dynamics. And well, in the long debate that occurred a few centuries ago between Sir Isaac Newton and Sir Robert Hooke, they were fighting most of the time in the Royal Society, one with the beautiful laws of dynamics. The force correspond to acceleration, and we can develop all the dynamics of mechanics. And coupling it with Hooke's law, we can start to build oscillations and waves. Well, today we have to go beyond the curtain and look at some part of the dynamics. Now, how to start? Again, and I will repeat it now for today's lecture, this is a very quick view of many topics that you will expand with Karim. So let's take it as a very simple approach. Well, let's call it, as a very simple description, a stick-slip process. Like the violin player. We're not playing a violin, okay. It's not such a simple but beautiful system, but something is applying force. We have friction. Friction is causing the system to stick. And then when the friction action is overcome by the dynamics, let's call it tectonics, we will have slip. So we have, again, 3 simple phases. Stress accumulation, tectonics. Stress is losing with friction, stick. Stress is overcoming friction, release. And during the release, we have rupture, and the rupture is causing seismic waves to propagate, to be generated and propagated. It's simple. We have time, stress building, faulting, and again. As I told you, this is not periodic. Why? Because, well, tectonic forces can be studied now with GPS. We can study the strain distributed over continental or regional or local systems, but still we don't know exactly this boundary condition. And please remember that our time window of investigation is relatively short. Let's say, I remember when with Karim, he was developing one of the first projects with GPS. Well, let's say that 20 years passed, and me and Karim are getting older, but 20 years is nothing compared to a sort of a cycle. It would be 100,000 of years. So we have a very tiny time window that we can open to study with a modern approach what we can call a cycle. So friction is here, stress accumulation is here, energy is released. Part of it is released by heat, part of it is released by mechanical energy, like seismic and sometimes tsunami waves. This is the energy balance, okay? Now, focusing on a single event, we can imagine to use the same approach that Harry Fielding Reid, back in 1906 in San Francisco, with some observation. Well, Reid was really great. He was a giant in discovering things because he was really founding seismology with the elastic rebound theory that is here summarized. So we have stress accumulation, friction is winning, friction is losing, slip. And let me play again. Let's see if I can play again this. So you can imagine to have two combs here. Well, I'm not using a comb, as you can imagine, but sooner or later, you're going to play the teeth of the combs. And energy is released. That's the earthquake. Let me tell you just now, also, if we're going to discuss a couple of slides at the end of this course, that Harry Fielding Reid was also one of the founders of forgotten fathers of side effects. And you will discuss side effects with Stefano Parolai during his course. So elastic rebound, it's a very simple concept, still valid in some part, and it can be easily seen, well, relatively easily seen, especially in California, where we have this strike, we are going to call it strike slip motion on the faults. You have many crustal areas, also in the desert there. It's relatively easy to see faults in California. It's much more difficult to study the faults in the Alps and the Apennines because most of them are blind faults, so they don't appear at the surface. But in some cases, we can see that, and we can see the tilt. So that's what we can call also the co-seismic slip. It's something that has been slipping and waiting for the stress to recharge, like a carillon, a musical carillon, okay? You're going to play this melody. And the music is, of course, earthquakes. Now, what about the fault? And this is what we have to try to study. Well, we can define it in a sort of with an easy wording as a surface across which slip occurs. And for pure tectonic events, and these are the ones that we're going to study, slip is parallel to the fault surface. Oh, this condition will become important from the next lecture, because actually this means that if you have the fault normal and the fault slip, let's call it U vector, they will be perpendicular. So the slip is parallel to the fault and so perpendicular to the fault normal. Another keyword for today is that the slip can develop only in a brittle environment, not in a ductile one. Ductile one will create shear zones where you have flow. What is deciding this transition between brittle and ductile? Well, different rheology will correspond to, yes, different materials, but different boundary conditions like temperature and pressure. It's a very complicated, interesting, but complicated thing. We will not enter into this. And of course, you can have a fault and you can have fault zones, so system of faults. So we have a huge set of faults, and from now on we will begin to focus on one, because we want to enter into the kinematic description of faults. By the way, remember, the one of the messages to take home today is a very simple one: the difference between brittle and ductile. In the Earth, there is a sort of a transition between these two regimes. And as I was telling you, okay, this transition is decided mainly by tectonic setting and depth. And this means composition, confining pressure, and temperature. Because if you apply the same force to a ductile system, you will not have a brittle behavior and with stick slip, but you can have flow. So you can have an offset, like in this case, but the deformation is accommodated in time with a flow and not with a slip. You can call this also a creep deformation. And we will rediscuss it, but from a different point of view when we will discuss about anelasticity. Okay, now some awardee slide saying that if you want to take a sort of a microscopic vision of what's occurring in a material when you apply a force, so you're applying a stress, well, we should go to sort of a solid state matter course and to study chemical bonds, but it's not our cup of tea. So as a qualitative description, we can say that if you use a sort of a microscopic, nanoscopic lens, and if you look inside a solid material, not inside of a gas, or you can study acoustic waves, but you're not going to have an earthquake in the air, you can have waves propagating in the air, but not earthquakes, or in a liquid, or in a fluid. But if you take a solid, you can have a complicated vision of what is a rock that is made by minerals, and minerals made by crystals, and made by entering with your lens. Okay, you have chemical bonds. And you can imagine to have this a system like a chalk, a piece of chalk in equilibrium. Now, if I take a chalk here, and if I apply a stress, sooner or later it will break. It's not going to flow, it's going to break in normal conditions with, let's say, atmospheric pressure with, let's say, 15 degrees. If you apply a stress, it can behave in a linear, elastic way, and then it's going to break. It's a brittle material. Some other material, if you take a rubber, piece of rubber here, I have one somewhere, but okay, you can imagine, you can apply, it's going to deform for very, how to say, it depends on the material, it depends on temperature, it depends on many things, but in normal temperatures, if you use a rubber, it's going to deform it's going to support strain much longer than a piece of chalk. Now, if you take steel, if you take a building, and if you take steel, for example, it can behave in a brittle way, but depending, according to temperature, it's going to flow. As if any artisan working with iron, hot iron, knows. So temperature is very, very important. And temperature and confining pressure will decide the transition between these different rheologies. Now, using some terminology that is about dynamics, we can say that every material has a linear behavior until a given limit. Then, sooner or later, the Hooke's law, the pictures are in the next slides, but let me anticipate it. Hooke's law is a line. Whenever you consider a force and a deformation, you have a line. And if you want to write it in the simplest form, and I'm sure that you use it to build the harmonic oscillator, Hooke's law is saying to you that the deformation is proportional to the applied force times a constant. You can imagine that it's the constant of a spring with a minus because it's a restoring force. but it's a line. And please do remember that in Hooke's law, we don't have time. Every action and reaction takes no time. You apply a force, you get a deformation. You remove a force, you go back to the equilibrium immediately. There is no time. And we're going to break this very efficient but simplistic approximation when we will speak about viscoelasticity to discuss attenuation. Here there is no time. And the elastic constant is a number with units. Please remember, in its simplest version, an elastic constant is what are the units of an elastic constant, my friends? It's not, okay, it's not a vector, it's not a tensor, it's a scalar, but with units. And for normal Hooke's law, it's Newton over meters. And if you take lambda and mu, that are the elastic constants for a pure Hookean solid, they are numbers, they are beautiful. One is a rigidity modulus, the other one is connected with the bulk modulus, but they are not pure numbers. Strain is a pure number. Stress has the units of pressure, so it's a force over an area. You can call it Pascal, you can call it bar, you can call atmosphere, you can call whatever. But please do remember that lambda and mu, the Lamé parameters, have units, and they have the same units of stress, because strain is a pure number. So please remember that in the classic standard Hooke's law, force is a force, x is a displacement, and k, the spring constant, is, of course, Newton over meters. But when you generalize Hooke's law, like for pure elasticity, for example, and the one that you have developed with LAPO to build P waves and S waves, please do remember that Lamé parameters, they have units and the units of stress, because strain is a pure number. It's a relative displacement. It's delta x over x, strain. Well, it's a tensor, but okay. So now, going back to our scheme here, when you overcome the Hookean limit, you have different reactions. The system can break, it's brittle, or it can deform in a plastic way. But this limit is called yield point. And what's going to happen after the yield point depends on the rheology, and in other terms, so the characteristic of the material, but also the ambient conditions, temperature and pressure. Now, what we're going to discuss today is that we're interested to the brittle mode, so fragile, if you want. And so an intact material is going to... Tell me.
I have a question. I have a question.
Please.
So the difference between I didn't get very well the difference. What is the difference between brittle and ductile? Still, okay, we can have a ductile material which can, if we apply a stress in a long time,
yes,
and if we get to the limit, it will become a brittle. It will break.
Definitely, so yes, my friend.
The difference is
no. Okay.
Time and temperature.
Wait. You are totally right. Temperature, pressure, and time will decide the reaction of this material. But and slides will come discussing this, not only today, but also when we will discuss about viscoelasticity. You're totally right. But for now, what I want to focus on is that the Hookean world universe is made by a line where no time exists. We have to go beyond this. And this is what we're going to do. So this is a wordy slide, but the pictures will come now, like this one. So this is what we are going to discuss today. And time will be will enter in, let's wait for 5 lectures. So your point is totally right. What I was simply showing here is a Hookean behavior. It's called elastic, pure elasticity, and reaction of a material will depend by many factors: temperature, confining pressure, material, and time. But wait for that. So give me some time to answer to your point, some time that could be 1 hour today, but also some lectures that are going to come. Okay, by the way, what I wanted to show is that every material, according to the strain and stress, will have an elastic limit. This is called yield. And what's going to happen for us today is that we have an elastic limit after which rupture will occur. And if you continue to apply the stress, once that the rupture is created, is that we will have frictional sliding along the fault. This is our topic for today, and that's the end. Well, it's not the end. So because we're going to spend some more slides about this, but this is, this is the dynamic framework where we're going to develop the kinematics from the next lecture. Okay, wait for the other considerations and especially time, because flow will be important. I've left a slide here discussing just this. Now, for example, some materials could behave not in a brittle way, but for example, we can have a plastic behavior. What's going to happen in a plastic behavior is that you're not going to have a fracture. So you're not going to break the material, but you are going to have a permanent deformation with flow. And if you remove the stress, you're not going back to the same point in the equilibrium, you will have a permanent deformation. Like when you take a spring and you go beyond its elastic limit and you're going to yield it, and then you're going, if you release the stress, it's not going back to the equilibrium. And please notice that when you consider a plane, Fx, force and distance, or stress and strain, the area that is left there corresponds to work and thus energy. Okay? Remember from high school physics, that infinitesimal work is a force times an infinitesimal displacement. And if you take the integral, you will have the work done on a material, and that will correspond to an area here. But in the Hookean limit, you're moving along the line, so you're not creating area. All the energy is conserved. Kinetic potential, the spring and the velocity. That's the harmonic oscillator. But when we go beyond the elastic limit, we create an area here, and if we don't go back, we are adding work to the system, that is the work needed to have a plastic deformation. Okay, so remember, brittle behavior is one possibility. Plastic behavior is another possibility. So you're not going to have a fracture here, but you have a permanent deformation. Maybe sooner or later, you will have a fracture or a flow, but the system will never go back to the equilibrium position. We have broken the harmonic oscillator. Remember that in the pure harmonic oscillator, we have a continuous exchange of energy, potential, kinetic. But in any realistic oscillator, we have also some dissipation. And dissipation means that at every cycle of oscillation, part of the energy is lost. Well, it's not lost, it's converted. For example, in temperature. Maybe if you're using a pendulum, sooner or later it's going to stop. and you have increased by some picodegrees the temperature of your room, and you need to recharge the pendulum. So we have many ways to go beyond the elastic Hookean world. One is to consider a different rheology, plastic, ductile, or to add some viscous component that will be a model of part of the energy to be lost. And we're going to develop this when we're going to speak about an elasticity, in the sense that when a wave is propagating inside the Earth, part of the energy is lost. Well, it's not lost, it's converted in something else. But please wait for that lecture when we will go deeper on that part, and time will appear. And we will speak about relaxed and unrelaxed elastic moduli that actually will have to be called unelastic moduli or viscoelastic moduli. So again, a different rheology. Okay, now a picture to relax you, relaxing in the viscoelastic sense, I hope, coming from the textbook that I was suggesting to you, that you can use as a sort of a shoulder.
Excuse me, Professor.
Yes?
Please, which slide are you showing? It's because I am only seeing the first slide.
Oh. The host has open breakout rooms. Okay, wait a second. Let me start again. I will stop sharing now and I will start again. Oh, I'm very sorry about that. Let me try to share the whole screen. Okay, wait. This is not for you. This is for a paper. This is for you. So wait a second. Have you been looking at these slides?
No.
Oh, God. So I was speaking to you, but with the same slides. So in the last 20 minutes, I was discussing this, then this, then this. Oh, so it was like a movie, but okay. The audio was continuing, but the screen was frozen. Okay. Yeah. Sorry for that. Please tell that to me. Yes. So now I understand also some questions, because you were stick to the Hookean part. And this was the discussion about the fault and the system of faults. Sorry about that, my friends. Okay. Please tell me. So thank you, but tell it to me before. Otherwise, I will like be an offset movie where the audio is changing, but the image is not. Okay. So this was the imaging of a fault, of a slip over the fault. So you had been missing this nice picture of a Harry Fielding Wright. Okay, there you go. This was the animation of the elastic rebound. Let me try to, let's see if I can play it. This was the metaphor that I was using of the two combs, and you're trying to slide them: stress accumulation, release, and mechanical energy. This was the picture that was showing, the intention is to show the difference between what is accumulation of stress and then for a brittle and then to have a shear. You have a deformation, but it's gradual. This is the difference between ductile and brittle, if you want. Slip, sudden slip, or not. Sorry about that. So I was speaking, this was the wordy slide, recoverable. Now I better understand your question. Sorry about that. So if you want, brittle behavior means that sooner or later you're going to break the system. Ductile is going to accommodate the deformation with flow. This is the main difference. And this was the most important picture for today. So let's see if I go to this. Okay, you're looking at that in a full screen, right? Is it okay? Okay, thank you. Thank you. Okay. So sorry about that. I was speaking without these pictures, actually. So this was the generalization of Hooke's law, in the sense that we have a strain here. It's like Hooke's law with X. Here we have stress. Actually, it's called differential stress because what is important is not the equilibrium stress. For example, if I take an object like a chalk here, well, actually it has some internal tension because it's also, when it is in equilibrium, all the forces here are balanced. Well, if I release it, it's going to fall under gravity, but okay, we have some internal forces. Now the differential stress is what I'm going to apply after the equilibrium. So we can imagine the Earth as a sort of a self-gravitating equilibrium system, and then we are going to study the differential stress from this equilibrium. So that's why here it is written differential. The limit, the elastic limit, is the yield point. And beyond that, a brittle material is going to break. So it's going to create a new accommodation to start again this cycle. And if you're going to apply again the stress and there is friction there, okay, it's going to accumulate and then stick, slip, slip, slip. So this is what is called frictional sliding along a fault. But on the other side, I was showing to you this, that was an example with the same axis, strain and stress, but with a different behavior. This is not a brittle behavior because you're not going to have a fracture, but you're going beyond the elastic limit and you're going to be elastoplastic. And if you remove the stress, well, in tectonics, this is not happening, the system will go back, but not exactly at the equilibrium point. So when I was mentioning an area created in this part, it's this hysteretic area, and it's the work done and left on the material with permanent deformation. Are you looking at this slide here about plastic and ductile behavior? Yes, good, thank you. Thank you.
Yes.
Okay, and now what I was telling to you, and we were stopping here, just to relax you, was to, here I'm using a picture coming from the Stein and West session textbook, but is showing mainly exactly what we've been discussing. And so we have on the left a possible brittle rheology, you see, strain and stress. Then elastic limit, fracture. And the chalk is broken. I cannot do anything else if not throw it away. Or we can have like rubber, then we have elastic, then we can go over the elastic, but it's not going to break, it's going to have a permanent deformation. If I release it, it will not go back to the equilibrium. And so you have something that you can call permanent strain there. Well, when you have a brittle regime, but of course, it means that you have a composition, you have a pressure, you have an initial temperature. Well, that is the realm of friction. And it's the realm of stick and slip behavior. And the strain rate is a very important factor. We had a feeling about this when we discussed the seismicity of Japan in one of the movies of the introductory lecture. Now, of course, inside the Earth, going deeper, you have different temperature, but especially confining pressure that is increasing because you have a lithostatic pressure of what is above your head if you enter inside the Earth. And this is changing. Okay, materials are changing, but also the confining pressure are changing. So at a given depth, the behavioral rocks is no more brittle, but it could be ductile and accommodate deformation in a different way. That's the transition that occurs at different depths between the brittle and ductile, if you want, lithosphere and asthenosphere. Again, this transition here will be discussed better in Karim's course. But again, in different conditions, in the past, so also in the time, you can have a different accommodation, and rocks can behave like fluids. What you need is also time, of course. And that's why in many cases, and we're going to use this one, Hooke's law is not enough. And maybe we have to use Newton's law, but not the Newton, the force is equal to the inertial mass times acceleration. That's the second law of dynamics, and we're going to use almost pretty much every day. But I'm referring to the Newton's law of Newtonian fluids, so purely viscous. And I decided to leave this, this cartoon here, this picture, because it's very nice. And please note that the axes are very similar to the Hooke's law. We have stress on the y here. We have strain, but pay attention because it's strain rate. So a purely viscous Newtonian fluid is behaving like Hooke's, but with a dot. And the slope of a straight line is called viscosity. And time is entering now. And if you take the air, water, oil, honey, or asthenosphere and lower mantle, you have a huge, view of different orders of magnitude of viscosity. So we can have, like in the lower mantle on the asthenosphere, such a huge value of viscosity, then on short time scales, it's behaving like a solid. And S waves are traveling inside the mantle. But on long time scales, this is behaving like a fluid. So it's going to accommodate also convection inside it. While on the top, in the lithosphere, viscosity is lower, is large, but is slower, and in time is going to break, not to flow. So rheology is very important. And I put this cartoon here. I updated it. So I will update you have to know that almost every day and every year, when I'm able to, I'm changing slides just with the hope to improve them. So, okay, if you see some slides that are not exactly the same on the PDF, that is now on the website, my intention is to update. Well, I will update when we finish the lecture, so you will have also an updated version. And this cartoon here is interesting because it's now putting in relation not only stress and strain, but stress and a different parameter that is the confining pressure. So at low values, if you take a material and you apply a stress, you're going to break it. If you're increasing the confining pressure, and this means in practice go deeper inside the earth, well, you have a sort of a transition zone, but at very large confining pressures, if you apply the same stress, well, actually, the behavior is not going to break, it's going to flow. So you can call it brittle, ductile, and semi-brittle in the middle. So according to the position on the Earth, if you go deeper, if you're in different tectonic regimes, you will have a given depth until which you have a brittle behavior and earthquakes are going to happen. A given depth beyond which ductile domain will be valid and you will have flow. And remember that confining pressure is an important parameter, but also time here, and thus viscosity is important. But so in different regimes, you can have, for example, in orogenic belts, you can have very deep earthquakes until the lithospheric erupts. In some places where you have stable regions, but they are called Cratonian regions, cratonic regions, you can have a thick pack of lithosphere. In some other parts, like oceanic ridges, you have a very thin, pretty much nothing at the beginning, and then you're going to thicken the brittle part. And in subduction, you're taking brittle material depth at the very important depths, and sooner or later, the recycling will start. So you see that these pictures here are something that we're not going to treat next in the course, because we will speak about kinematics of the rupture. But you do understand that this is a dynamic framework of what's going on. Brittle, ductile. Okay, and a picture showing that under these different rheologies, we may have different behaviors. In practice, because this is rock mechanics, and you're going to discuss this with Karim. I never participated to an experiment, but I can imagine it. So you take a sample, and we're going to use it later in theory. We take a sample, we apply a confining pressure, we apply compression or traction, and sooner or later it's going to break. Well, in given confining pressures at different temperatures, it's going to flow. So according to the tectonic regimes, compressive, tensional, or shearing, we may have folding, shearing, stretching, and thinning, and this is beautiful for geologists. But what we want to understand is that we can have folding, and we can have thrust, normal, and strike-slip folds. That's the pictorial message to take home today. And one of these will be an earthquake. And of course, in time, it could be a series of earthquakes, because you break it, and then later you will have frictional sliding. Okay, now let's imagine. Oops, what's happening here? Now let's imagine how to say, ideal experiment. Karim, my internet connection is unstable. I'm getting this. Do you copy me? Do you hear me?
Yes.
Good, because sometimes I'm getting some warnings here. I'm using the university Wi-Fi with this. Okay, university is not so powerful and rich as ICTP, but we should have a sort of a stable connection here. So let's hope that we can perform here. Now, let's imagine to take a sample. Let's imagine to perform some experiments. As I was telling you, I never did it in practice. I've never done that in practice. Ask Karim. But let's try to understand what's happening here. So maybe we know stresses. We take a sample, an intact one. We apply, for example, a compression. We can imagine that now we have at the beginning, we have a Hookean behavior. So we compress, we release, it's going back to the equilibrium, like a spring. But sooner or later, when we go beyond, we will have microcracks appearing, and then they coalesce into a fold, and we're going to have a sliding. And this is what's going to happen in laboratory and in nature. Let's try to understand what's going on here. And we can say that from a sort of a microscopic point of view, a different hierarchy of cracks will appear, and then there will be a jump in this hierarchy, and the fold will form, and we can have a slip. Now, can we try to understand from these experiments and to make some conjectures about the angles of this rupture, the style of this rupture? Well, with these stress arrows, since we have a confining stress and we're pushing from the top, our intuition is enough. We're going to wait about a fault, let's call it a fault in the material. Can we predict, can we explain the angles of a fault? Well, in practice, what we see is that actually the fault plane can be created in this direction or in the other one with an angle that is not 45 degrees from, let's call it sigma 2 and sigma 1, but is going to be nearer to sigma 1, to the principal one. Can we try to guess why this is happening? Well, the answer is yes. And the only formulas, well, not exactly the only ones, but the most important expressions that we're going to use today are this. And these are the basic rules, and the only ones that you will study with me about dynamics. And they are very old. Actually, they are so old that also if we have no proof about a written text, that Leonardo da Vinci was one and Galileo Galilei were the first to study friction. But the first one to, how to say, to express it with a sort of a law is the Coulomb, who formulated a failure criterion that is very simple, actually. You have to imagine to have a piece of something here, or better, let's imagine that we have a plane, we have a mass over it, and we have friction. So it's taking back us to high school physics. Here we have an angle. We have a friction. Of course, if no friction, the mass will slide immediately. But if we have friction, we will have a normal component, we will have a coefficient of friction here, and according to the angle of the plane, the mass will stay or will slide. Okay. It's the same idea, actually, that Coulomb developed. And he was saying that, okay, if you take a piece of rock, you will have fracture only when the differential stress, the shear stress, will overcome a quantity that depends on this coefficient C, that is called cohesion, plus the normal component times the coefficient of friction. If you overcome it, slide, slide, fracture. Easy. Of course, if you want to explain this very simple rule from the point of view of theoretical physics, we will need to go to a scale that belongs to solid state physics. But I cannot. But if you work at ICTP, there are many researchers that could help you in this. But from the continuum mechanics point of view, that's enough. Then we have an additional stuff that is called Hamilton's second law. Because once that the material is broken and you created a fault or a sliding surface, well, then cohesion is lost and the C term disappears and you have this coefficient of friction. And you can imagine when you want to push a material on the pavement, at the beginning, you have to push it to overcome friction. But once that it is in motion, it's easier to make it move. And sometimes it's the difference between static and kinematic friction. Well, it's the same. The only difference here for Hamilton's law is that cohesion is lost, also because the material is broken. And then in the 1950s, a set of experiments began to be developed there, and they can be summarized in a very important and simple rule that is called Byerlee's law. Then he had been studying a lot of crustal materials at different depths, different temperatures, and the summary is the following here. It's a Byerlee's law. It's very similar to Coulomb, theoretical, law, but this was done with samples. And you see the structure, a quantity, cohesion, a slope, friction, and stress. So if you want to stay on the safe side, simple side of full dynamics, that's enough. So it's Coulomb, very simple. But if we want to go deeper on this theme, well, that's a tough walk. You will develop part of it again in Karim's course. Now the boring part for today. Sorry for that. How to use what we know, trying to understand, or better, to visualize what's occurring there. Well, we have to go back to the definition of stress. And you did it with Lapo, right? Please make me like that. You define stress with Lapo, right? Okay, good. Now, if you do remember, the strain tensor is symmetric by definition. The stress tensor is also symmetric. It's a little bit more tricky, but it's a consequence of the energy and momentum conservation, but it's symmetric. And every time that you have a second rank tensor that is symmetric, you can diagonalize it. And you can use what we call the principal reference axis, and all the elements of this 9 elements matrix stay on the diagonal. You can call them eigenvalues if you want. If you stay there, you have only the diagonal terms. If you want to change the reference system, of course, now the other elements appear. Still, it's a symmetric tensor. And to make this change of reference system, what you have to do is to make a rotation. And the rotation, in this example here, that is coming again from the Steinway session textbook, this is a 2D version of a 3D problem, but nothing is going to change in practice, is that when you perform a rotation, actually, you can decide an angle of rotation, and what was oriented in the principal stress direction, well, it will become, after rotation, after this manipulation here, this beautiful matrix that I never, and I will never remember. But, and this is the nice part, Sir Otto Mohr, if I'm okay, he was saying, wait a second. Because if we use a little bit of trigonometric expressions, we can simplify that messy order of sines and cosines. And now, if we take a piece of material with its internal stresses, and we can imagine that, okay, in the principal system, we have only the diagonal terms. In the principal system, we have only normal stresses. If we rotate by an angle theta, like in this case here, well, now also the other stresses will appear, for example, the shear ones. Now, if you want to write the normal stress at the surface, making a theta angle compared to the principal axis, and the shear stress, so these two ones, and if you're going to write them using the previous matrix, actually, you can write it easily using what? Using the principal stresses and these two angles. Now you could say, so what? Is it simpler than previous? Well, yes, because now we have a very nice way and simple way to represent the stresses on a body. Using what? Using this angle and using the principal stresses. And using the relation between sine and cosine, we can plot what is called the Mohr's circle. And it is like that. And using this circle here, let me try to, let's see if I can squeeze it. Okay, so I can see the whole plot. Now what we can do here is to have a synthetic view of what's going on a point of a material. Using what? Well, the axes are the shear stress and the normal stress. Using what? The angle respect to the principal directions. You take it twice and you rotate on this circle here. And you can read, according to the rotation, what are the stresses that are upon that point. Of course, if the angle is 0 or pi here, you will have just the normal ones. And it will be the maximum or the minimum. In any other angle, you will have a part of a shear stress. So actually, the definition of stress, it's symmetry. It's symmetric nature. The way that we can diagonalize it, the way that we can rotate it can be summarized here. Now, you could ask, what should we do with this? Should we use it? Well, now, what is deciding the stress of a material? Well, the confining pressure, for example. And then we can use this circle here to see what's going to happen when we apply experiments. So let's imagine, for example, that we apply a sigma 2 compression as a confining word, and now we begin to push the material with sigma 1. This circle is going to change what? Sigma 2 maybe will stay fixed. Sigma 1 will increase. The radius of this circle will increase because sigma 1 is increasing. Oh, one warning here. Standing one session use a notation that is called a sort of a physical notation where compressive stresses are negative. In many geological textbooks that usually I don't read, but I know, or some geotechnical ones, please remember that compressional stresses are positive, and you have to flip this picture on the other side. So I'm using here the Steinway session notation. In some other pictures, I'm using the other one. Let's try to be elastic, and we can flip it very rapidly between the two. Here we have to imagine the compressive regime. So now we can use the Mohr's circle that is telling us what's going to happen. How to describe the state of stress of a body. And let's imagine to perform our experiments. Can we find something here? Oops, wait a second. Okay, so now we can imagine to perform some of them. Some of them are very interesting for us. For example, these two. So let's imagine that we are creating in 3D now, sigma 1, sigma 2, sigma 3, a confining word, and then we apply a compression and we break. In the other side, we can apply an extension and we break. Or maybe no confining pressure, but this is more important for material science or for people that is going to design buildings when you're trying to use steel and concrete to do experiments. But actually, we can imagine this, and these are called triaxial deformation experiments. Can we understand when and how material will break? Okay, one example here. Okay, for example, axial compression, axial extension, tensile. Now these experiments can be reproduced using the Mohr's circle. For example, the tensile, now this is a geological notation. Tensile is negative, and you see you have something that is pushing the system, and so the experiment means that you're going to enlarge this circle here. This is uniaxial. Or in this case here, well, actually, we have a confining pressure, And then we have sigma 1, but maybe we push or we pull. Can we get something from experiments here? Yes, we can. Having this in mind, especially from this one. What's going to happen is that now we have to imagine to take a sample, place it, applying confining pressure, applying sigma 1, break it, and we throw it away. Then we take a new one, we apply a larger confining pressure, we push, we break it, and we throw it away. And what we see here is that actually the fracture law is a line. And this is exactly, well, exactly. In my simple dynamic word is the Coulomb failure criterion. Because a line can be described by two parameters, the slope and the intercept. And the intercept will correspond to cohesion. And the slope will correspond to the angle of friction. So the Coulomb failure criterion can be found not only from intuition, deductive word, but also from the experimental one. Well, and that's enough for me and you, because there is people devoting courses to this, not me. You can complete this picture with many other things. But what we need today is this Coulomb failure envelope. It will depend upon what? Well, of course, the shear stress, the normal stress, the material, and temperature and pressure. But we can get a line here with two parameters, cohesion and slope, cohesion and friction, just two parameters. Now, this cartoon, this plot here, applies to samples that are supposed to be intact at the beginning. We break them, we throw, we take another one. Now, can you imagine what's going to happen if I don't replace the material? I break it and I continue to apply stress. There is a course, you can take a course about this. But for today and for my course, that is more devoted to kinematics, my question has to be intended in a very simple way. Can you imagine what's going to happen if you don't replace the sample and you continue to apply stress? Well, actually, if the sample is broken, cohesion is lost. So the C term disappears. So it's like if you take a line and now you drop it. Slope is also changing, but you drop it. What does it mean? Is that now the shear force that you have to apply to create sliding is lower. And what does it mean in very simple, maybe two simple words, but these are the only words that I know, is that once you create a fold, it's more convenient for the system to slide on a pre-existing fold than creating new ones. So, because cohesion is lost. And this is the message that we have to take, the most important message that we have to take home. But of course, remember, I'm cutting a long story short because our story will be different. It will not be a dynamic story, it will be a kinematic story. So take this just as a prequel of what we can develop better in other courses. So this is a sort of the animation of what I was trying to say. You can imagine to take the system, apply confining pressure and increasing sigma 1. You're going to enlarge the radius of a Mohr's circle and then break. You throw it away. And then you start from another condition with larger confining pressure. You increase, you have to increase larger. But then you break and you throw it away. Then you take the third. Oh, sorry, the third was lost. But now the idea is building that low. This is what I was saying to you. So that's the summary of the most important feature that I wanted to communicate to you. So the Coulomb's law of failure, it's a conceptual, simple law. It's also an experimental law. And now sigma 0 could be the cohesive strength that belongs to an intact material. The tangent of a tangle can be called the coefficient of internal friction, and it's due to friction. Sigma n is the normal stress. Remember the analogy with the mass on a plane, inclined plane. And then, of course, you have to reach a critical stress required to break the material. Simple. Now let's try to apply this concept to earthquakes in some way. Well, for example, you can take many materials. They may be representative of some materials at the surface of the Earth. Again, this is a sort of a sketch that is summarizing to you that if you go here into tensile experiments of these materials, you go to the negative part, you see it's not a line, this is a part of a circle of a parabola, but we're not interested to that. We're interested here, the different materials can have different slopes and different cohesions. So material is one parameter that is important to decide the failure criterion. And the summary can be found in this, again, we can call it Mohr because we're using the Otto Mohr representation of shear and stress. We are using the Coulomb because we are creating an envelope, at least in the part that we're interested to. And we can imagine that the three samples that we have been breaking, so they were reaching the elastic limit, failure, it was the first. So it was here with small confining pressure. Then we throw it away. Then we take the second, larger confining pressure, and later is breaking, and we throw it away. And then the third. So now you do understand that, for example, the Hookean behavior and its transition to the fracture depends on the confining pressure. There is another important feature that people
please,
working.
Professor, I have a question.
Yes, please. Yes, go on.
Are you saying that? Are you saying that at each time we have, when the material break, we have to replace it, and we have to replace it by the same material, or not?
Oh yes, 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 yes. Okay, remember, I understand your point. Remember, this course is theoretical seismology. So what I want to say is that what we're doing here is a conceptual experiment. But what people, for example, two buildings above mine here. Yes, please go on. Please.
I just wanted to say why, if we replace it by the same material, why we would have different critical
because now stress. Because now the material, you have to imagine, you can take this piece of chalk, sorry for my silly example here, but you're not doing a tensile experiment, you're doing an axial experiment. So you surround it. Let me try to say it again. This is the kind of experiment that we are performing there. It's not a free material and just a tensile experiment. We apply a confining pressure. So in the experiments, in the next ones, what we're doing here is that sigma 2 and sigma 3 is supposed to be equal to sigma 2 is increasing to the next experiment. So we are not doing, we are using the same sample. Oops.
Okay, we change sigma
then,
2.
Yes, we increase it. If you increase sigma 2, then you're moving
sigma 2 and sigma 3.
Sigma 2 is supposed here to be equal to sigma 3. So sigma 2 is increasing, and now we have to increase sigma 1 to break the same material. Getting? Oh, sorry. You have to give me 1 minute. I have to charge my Mac. My power cord is on the other room. 1 minute while you're thinking about this. Okay, energy for my old Mac, but not for me. Okay, so is it charging? Yes. So I hope that I've answered to you. Sigma 2 is increasing. So we are moving on this axis here. So this was the animation here. First experiment, you increase sigma 1, but you see sigma 2 is fixed here. Break. We throw it away. The second experiment is performed at larger sigma 2. So we have moved from here to here. Have you got the point? Let me close the door.
Yes.
So we are using the same material, but different confining pressures, increasing. That's why sigma 1 has to increase. The idea is to go deeper inside the Earth, because lithostatic pressure will increase getting down into the Earth. So also temperature is changing, but for this criterion, temperature is not important. So I hope that I've answered to you. So the summary was here, and what I wanted to say.
Thank you, Professor.
Okay, thank you for your question. What I'm trying to say here, that remember that in the, how to say, more realistic world, there are some other effects. Like, for example, you can take a regional stress here, but you can also imagine to have some fluids inside the material. And you can imagine that the fluid is trying to win the confining pressure, because it has, a fluid can support pressure. So the net effect of having fluids here is that actually you're taking your Mohr's circle and you're moving it to the left. So it's diminishing the confining pressure because part of it is won by fluids. And if you diminish here the effective confining pressure, actually the material can break sooner because you're moving the circle back here, and so the failure criterion can occur there. This is one message. Please don't stay just on what I'm showing to you, but please, if you have to go deeper inside this topic, that is rock mechanics or whatever you call it, again, there are many ways to go beyond what we are looking here. So it's just a panoramic view. Then this is the other important message that I was trying to give to you, is that the Coulomb failure intact samples. But now if you take the sample and you don't throw it away and you keep it, cohesion is lost, and now the line is different. What does it mean in practice? That actually you have two contact points where you can have sliding before to reach that original sigma 1. So it can slide before on existing faults. This is a physical, simple message to you. Now let's try to put order in what we have said. And also, so we have seen the Coulomb failure criterion, the Edmonton's law, if you want, when the material has lost coherence. And the last part was to show to you some pictures about the third and last law that was about fracture in materials, that was Byerly. And Byerly was collecting information about a lot of real materials. So here I put the original plots by Byerly, and you see, well, the scatter is large, but he decided to investigate some crustal materials at different confining pressures, and he was finding regression lines with angles of sliding friction. So basic dynamics can refer to Coulomb, Edmonton, Byerly. Now let's try to make some order. And let's try to conclude. I'm sorry, guys. As usual, I will steal from you 10 minutes to conclude this part, because on Friday we have to move to the kinematics. Some quick messages here. Remember that the behavior of a material can change with confining pressure. This is an example. If you take one material, like chrome point, like a kind of limestone, and if you study the rheology, differential stress and strain, you see yield, fracture, sliding. Well, it depends definitely on the confining pressure, if you want different depths. So first message, parallel message. Second, the presence of fluid pressure. For example, this is sandstone, differential stress and strain, and you see how these rheological curves depend according with the fluid, for example. Another feature to be considered in practice, not with me, but in practice. Third, temperature. Because if you take, again, the differential stress and strain, of course, you may have a brittle behavior with fracture, brittle plastic behavior, and then plastic ductile behavior. Remember, all these factors enter inside the dynamic game, and we will forget about them with me, not with Corinne. And now let's try to recap everything here, and let's try to put these ideas back to the Earth and to the earthquakes. What is, and you can call this at the end, the Anderson's theory of faulting. It's very simple. It's quite relaxing. Now, what is saying Anderson? What was saying? Well, okay, if we take the surface of the Earth, we considered, and we have used it, you used it. What's happening here? Update by, no, I don't care about this. Adobe, okay. The surface of the Earth in many problems is considered as a boundary condition as a free surface. And you have used it, also if you have not performed the course with me, but when you discuss the free surface of the Earth for surface waves, you have said, okay, the top of the Earth is a free surface. What is a free surface? Well, the normal components of a stress are, we're not doing fluid mechanics, so gravity is not there. But free surface means that, okay, please tell it to me. What is a free surface? What is a free surface? I don't have a glass of water here, but let's imagine to pour some water inside a pot. You shake it, then the liquid is going to go back for the equilibrium, and it's going to create a free surface in the sense that it's an equilibrium surface, and the vertical component of the stresses is balanced, otherwise you will have motion, gravity waves. But especially you have only the normal one because the shear stresses have to be zero. That's the definition of a free surface. The normal components of the stresses are zero. What does it mean? Well, it has to be a principal axis of stress. Remember, principal axis, you have only normal and zero shear. So it has to be a principal axis. Which one? Well, it could be the largest, sigma 1, could be the smallest, sigma 3, or it could be the intermediate, sigma 2. Now, what does it mean? That we have simplifying things, free tectonic regimes. The first one, if the vertical axis is the largest, so sigma 1 is this one, with this environment where you have smaller ones, you will have, this will correspond to a sort of the extensional tectonic domain, and what's going to happen, it will be a normal fault. The fracture, it's going to be like this. Vice versa, we can imagine that it is the smallest, so the compressive will be the largest, and we will have reverse faults. Or it could be the intermediate one, and so we will have, let's say, strike slip ones. So all the things that we discussed before in the Anderson theory of faulting can summarize that if you have at the beginning an intact Earth, according to the tectonic regimes, sigma 1, sigma 2, sigma 3, normal, reverse, strike. Now, let me leave to you, since time is really running short, and homework. We will conclude this with very nice pictures now, but your homework is very easy. Here, I'm writing combined with an angle of failure of 30 degrees. The 30 degrees appeared also here in my messy lecture. What is it? Here. Now, I've not told you explicitly where this is coming from, but you can deduce it from, this is hidden, from this. Your homework is to understand and to explain to me, well, not why 30, but okay, something like that. You see it here. It's very easy, it takes 5 minutes, don't worry. But since I don't want to steal too much time from you, I want you to understand why I was putting here 30 before, couple it with the Coulomb failure criterion. While for today, what we're going to do is to conclude this lecture, and as a definitely summary for today's very quick, maybe too quick, walk through dynamics, earthquake dynamics, this is what you have to remember. The rheology and friction and brittle behavior actually has been summarized with the Coulomb failure criterion. That's fine, or with Amonton's law. But we have to remember that friction and slip behavior depends on many other things, like, for example, slip velocity, temperatures, confining pressure, and so on. But we can summarize everything with Anderson theory of faulting, that pictorially is summarized here. Normal, thrust, or reverse, and strike. And we can make beautiful pictures of this. Nice. And once we know that a surface, a plane of fracture is going to be created, now we can also have a sort of a geological approach and try to describe it. And by terminology, and we will start from this terminology on the next lecture, and we will use the focal mechanism definition using this terminology, it's time to start with some definitions. For example, if we have a plane where slip is going to occur, we can imagine to describe the plane with two angles, as I was telling you. One angle will be called the strike of a fault. The other angle will be called the dip of a fault. And the motion will be the hanging wall respect to the foot wall, thrust and normal. Now, how to describe this? Okay, with this strike angle. As a reference, it's just a geographical description of one of the two angles defining a fault. It's measured respect to the north. It's an angle. Okay, and you can see it here. The second angle is telling us how the fault plane is evolving inside the earth, and it's called the dip. It could be between 0, it's a sort of a paradox, until 90. More than 90, you have to change the strike. So 0, 90 degrees, strike 0, 360. And these two angles define a fault plane. There is a third important angle that is telling us in which direction the hanging wall is moving respect to the foot wall. And this is maybe the most important angle, is called slip angle or rake. In many geological textbooks, it's called rake. It could be 0, and then you will have a strike slip right lateral. Could be 90, and then you will have a thrust. Could be 180, it will be a left. And could be 270, you will have a normal. So you see that the dynamics are deciding strike, dip, and rake, but then we will forget the dynamics and we will try to describe the rupture process on a fault given by two angles, and the third one that is telling us the slip. Now wait a second. The slip is a vector. So this means that it has a direction and also an amplitude. Keep it in mind, because this quantity here will appear in the definition of what we are going to call the seismic moment. Maybe the most important quantity of this course. And I will write it now at the end of the story. Then, of course, for terminology, we need other two names, but they are used, for example, in hazard assessment. Okay, we can define the hypocenter, so it's better to say the nucleation point, actually. That is the place on the fault where the rupture is starting. And if you imagine the projection at the surface, we can call it the epicenter. So something like that. But please, final message for today, that it was also the initial message, that actually the story is much more complicated. The fault, okay, can be a surface more complicated than a plane, but we will use a plane. Rupture will start from a point, you can call it the hypocenter, it's better to use it focus or nucleation point. Rupture will start, and these arrows here are the slip field that has a direction and has an amplitude. So rupture is much more complicated. But what we try to do today, and this is the summary for me today. Now let me try to stop sharing this, and I want to write something to this blackboard here. So what we did today was something very fast, a very fast passage inside the dynamics tunnel, where we have been learning about the Coulomb criterion, the Mohr circle, the fact that a sample is going to break with given angles, preferred angles, and it's going to break on surfaces that can be described by a strike angle, a dip angle, and then a slip angle. That's the dynamic definition inside the dynamic framework. From the next lecture, we will forget about dynamics. We will start the kinematics. So trying to describe what's going on. Let me tell you, as a final message for today, well, the area, it's better. After the terrible journey that we will take in kinematics, we will discover this quantity here. It's called seismic moment. It will be defined. It can be defined like that. Okay, I did it. But I want you to understand why it's defined like that. Because this quantity here is inside the new definition of, well, new, after 1977, definition of magnitude. And the only way to understand why it's defined like that and where it's coming from is to go through the representation theorem. And this is what we're going to do on Friday. Now look here, because we can understand also by intuition what is here. Rigidity modulus. Why shear stress? Remember Coulomb, the shear stress. What is this A? Well, that will be the area interested by the rupture. If you look back at my previous slide, it's there. What is this? That's the average slip over the area interested by the rupture. This will come from an integral of the last picture that I've shown to you today. That was also the first picture that I was showing to you today. So sorry, my friends, I've been running late again. But conceptually, we can start on Friday the terrible journey within the representation theorem. I promise yourself and myself to update, if necessary, the Moodle website with the new PDF. And Aurora, I will provide you the link to the seismology course mapped at the University of Trieste that will be, how to say, sort of a mirror of the ICTP one as soon as possible. Okay? So the next lecture, I don't know if I will be at ICTP or University or Lost in Space. Yes, tell me. Pardon?
Just a suggestion for next lessons. We couldn't hear you very well sometimes during the course, during the lesson. So I don't know if it's due to the Wi-Fi or
maybe the pure connection. Okay, let me tell you that
sometimes your voice was cutted.
Okay,
yeah.
Probably it's due to some, okay. Let me tell you that, for example, at my home, my Wi-Fi is much more efficient than the university one, but okay. I will do my best. I will do my best. Okay, thank you for the information.
Okay, okay. And well, also...
And also?
The assignment that you gave us, I didn't hear you very well.
Okay, let me tell you again. In one of the concluding slides about the Anderson theory of faulting, I had been writing. Oh, let me show it to you again. Oh, this is an hidden slide. The solution is here. Okay. You see, here I was saying combined with an angle of failure of 30 degrees from sigma 1, and then this, this, and this. My question to you is the following. Where this 30 degrees is coming from? Actually, there is another slide where I was using it.
Yes.
This one. Now, the solution to my question actually is easy because it's here. But I want you to think about and to join that statement and to tell me why the angle at which the possible fracture planes are forming are not 45 degrees between sigma 3 and sigma 1, but why they are near to sigma 1. Have you got my question?
Your voice is always steady.
Well, actually, I'm not listening to you. Sorry, I don't hear you now because maybe, let me ask it again. I want you to explain why in this slide here, I was writing an angle of failure. I want you to explain this statement. So why 30 and not 45? Okay? Okay, my friends, it's time to salute you. We've been running late. It's my fault. My fault, not a fault, but fault. Okay. And we're going to develop the kinematic theory on the fault. It will be tough on Friday, okay? So let me stop sharing. Let me salute you with a beautiful writing of seismic moment here. Oh, another tiny homework for you. I want you to compute the units. It takes 20 seconds. Okay? So we will start from that, from your answers. It's very informal homework. During wave physics, when I was giving that course, I was asking a little bit more formal homework. This is totally informal. Okay? Just think about it. Okay, my friends, let me salute you and let's leave this room. Have a nice lunch, have a nice day, have a nice everything till Friday. Okay,
Bye.
bye.
Bye. Bye.